The power that's inside. 9.3, geometric sequence. Last section was arithmetic sequences. This section, geometric sequences. There's a main difference between the two. All right, a geometric sequence is a sequence in which each term equals a constant multiplied or divide by the preceding term. So you're multiplying or dividing to get to the next term. Remember, arithmetic sequences were when you added or subtracted. So now let's see a geometric sequence. This one's a pretty simple one. 3, 6, 12, 24, 48. It looks like we are multiplying by 2 every single time. So if I ask you to find the next term, that's pretty easy. Multiply by 2 to 48, you get 96. But what happens if I ask for the 20th term? You can keep multiplying 96 times 2 times 2 times 2 times 2 until you get to the 20th term. But that's a lot of work. What if on the test I ask for the 100th term? You're not going to sit there and keep multiplying it by 2 until you get to the 100th term. That's a lot of work. So obviously there is a formula. There it is, the formula, the nth term of a geometric sequence. That would be the nth term. What we're looking for, A1 is the first term. The n is the number of terms. And then the r is called the common ratio. That's the number you multiply to get to the next number, the common ratio. So here it is. Fill it in. We're looking for the 20th term, so a sub 20. A1 is the first term, which is 3. The r is the common ratio. We're multiplying 2 every single time. And then here's the 20th term, the number of terms that we're looking for. All right, so filling in the formula, this is what we have. Then you have to use PEMDAS to simplify it or solve. Always do the exponent first. So 20 minus 1. And then next, we're going to go ahead and do 2 to the 19th first. And then on your calculator, 2 to the 19th is a pretty big number. And then the very last thing is you're going to do is multiply it with that 3. And it turns out that if you kept on doing it, the 20th term will be 1,572,864. Kind of cool. All right, let's do an example. Is this an arithmetic sequence? Is it an arithmetic sequence, or is it a geometric sequence, or it might be neither? So you're going from 16 to 12 to 9, so it's going down. Are we subtracting? Let's see, 16 to 12, that is minus 4. And then from 12 to 9, that is minus 3. And then from 9 to 6.75, that's something else. So it's not arithmetic. We're not subtracting anything that is consistent. Let's see, are we multiplying or maybe dividing something that's consistent? Well, to figure that out, we can go ahead and do this divided by that. On your calculator, if you do 5.0625 divided by 6.75, you should get 0.75. Maybe do that to this one and see what happens. Calculator, 6.75 divided by 9, it got 0.75 again. Do it to this one, 9 divided by 12, 0.75. All right, so it looks like we have a geometric sequence with a common ratio of 0.75. All right, let's go ahead and write a general equation. There's the general equation is just filling in everything except for the n, because we're not asked to look for a certain n yet. And so I filled in the first term, I filled in the common ratio, and that's it. Now I'm asked to find the 10th term. So let's go ahead and fill in the general equation for the 10th term. The only thing I did was I put 10 into the n. Do the exponent first, and then the 16 last. And there you have it. The 10th term is going to be 1.2041. All right, kind of cool, kind of fun. Ooh, this one says tricky. And again, it's only tricky because it's fractions. Is this an arithmetic, geometric, or neither? So if you look, you can kind of tell that you're multiplying it by 1/3, multiplying it by 1/3, multiplying it by 1/3. So it looks like you're multiplying it by 1/3 every time, which makes it a geometric sequence when you multiply. You can also say divide by 3. That works as well. All right, so our common ratio is 1/3. Write the general equation. There it is. I just plugged everything in except for the n. And go ahead and find the 10th term. Plug in the 10. Do the exponent first. And it looks like we have 1 over 19,683. I guess that wasn't too difficult. It wasn't that tricky. The only thing was we had fractions in it, so not too bad. Going backwards. What do you mean going backwards? The number 34,816 is a term in the geometric sequence, with the first term being 17 and the common ratio being 2. Which term is it? So what this problem is saying is you have the first term is 17, the common ratio is 2, that means you're multiplying it by 2. So the next one's 34, the next one's 68. And then somewhere along the lines, all the way at the end, you have a 34,816. The question is, how far down the line did you have to go to get that 34,816? What term is it? All right, so let's go ahead and do that. Here's our formula for geometric sequence. Let's fill in everything we know. We know the last term is 34,816. We know the first term is 17, and we know the common ratio is 2. So let's plug all of that in. And then we're going to go ahead and use what we know to solve for n. First thing you're going to do, get rid of that 17. Remember, don't multiply these two together. You cannot multiply the 17 and the 2 because the 2 has that exponent attached to it. So you cannot combine the 17 and the 2. But instead, we're going to divide the 17 to the other side. All right, so that's what we have. Now we have to solve for n. Guess what? Our n is in the exponent. We just did a chapter where we have to solve the variable when it is in the exponent using logarithms. So yes, logarithms are back. They did not go away. We're going to still use them. So how do you use logarithms to solve for exponents? This is an exponential form. Change it to logarithmic form. There it is. It was that left, right, left thing we did before, but in this case, it's left, right, left, right. So a little bit backwards. Go ahead and go back to your log notes to see how you change from exponential form to log form. But there it is. log base 2 of 2048 is equal to n minus 1. This can either be done in your head or a calculator, your choice. It turns out that it's just 11. Add 1 to both sides, n equals 12. So it turns out that 34,816 is the 12th term. You'd have to go 12 terms down to find that number. All right, kind of cool. I like this problem. You get to use information from the past. All right, moving on. Geometric mean. In the geometric sequence, find the two numbers between 7 and 875. So basically, you have a sequence. Somewhere along the lines, there's a 7, a blank, and an 875. So we're just trying to find the two numbers that are in between. So what do you have to multiply to get this number? Multiply to get this number, and then multiply to get 875. It is tricky. It says geometric sequence, so we are going to use our geometric sequence formula. Fill in everything we know. This is the last term, 875. This is the first term, 7. We don't know r, the common ratio, the thing we're multiplying every time. But we do know n. The n must match this n. And since this is 875, the n is the 1, 2, 3, 4th term, so your end is 4. Okay, let me erase that a little bit and plug everything in. 875 equals 7 times r to the 4 minus 1. Go ahead and do the 4 minus 1. We're going to go ahead and get rid of the 7 by dividing the 7 to the other side. All right, and this problem, you don't use logs because the variable is not in the exponent. We only use logs when the variable is in the exponent. In this case, we just use regular math. How do you get rid of a 3? How do you get rid of a third power? You cube root both sides. Cube root. And it turns out that r is equal to 5. And then using that r, plug it back in. 7 times 5, 35. 35 times 5, 175. And then just to check your answer, 175 times 5 is 875. How fun. Let's do another one of those. This one, find the geometric mean between 48 and 3. So this one only has one blank in the middle. All right. In the arithmetic sequence, when there was one blank, you just had to find the average. But when it's geometric, finding the average does not work. So it's a little bit trickier. You have to say 48 times what gives you that number, and then times that number gives you 3. And it looks like we might be dividing since it's going down, or multiplying by a fraction for the number to go down. All right, using the geometric formula, we have that. We know the last term is 3. We know the first term is 48. We don't know r, but we know the n. It has to match this n, which is this number. It is the 1, 2, 3rd number, so n is 3. There it is. Let's go ahead and simplify the exponent. 3 minus 1 is obviously 2. Divide the 48 to the other side. I'm going to leave it as a fraction. And then to solve for r, what do we do? What do we do? We square root both sides. When you square root both sides, you get 1/4. But you have to remember, there's something else you had to do when you square rooted both sides. It was plus or minus. So remember that from algebra 2. Whenever you square root both sides, it's plus or minus. And here's how it works. Let's go ahead and do the positive 1/4 first. What's positive 1/4 times 48? 12. What's positive 12 times 1/4? 3. That works. But let's do it with negative 1/4. 48 times a negative 1/4 is a negative 12. And a negative 12 times a negative 1/4, positive 3. So don't forget, when you have square rooting both sides, there's 2 possible answers. Fun. Last one for the day. This one says tricky. Find 3 geometric means between 27 and 2,187. So we have to have 3 blanks in there. Using the formula, plug in everything we know. The last term is 2187. The first term is 27. And then the n is 5 because there are 5 terms there. Do the exponent. Divide both sides by 27. So far, everything looks the same. It doesn't look that tricky. But here's what happens. How do you get rid of the 4th power? You 4th root. When you 4th root, it is plus or minus 3, which is the same as the last problem. So why is this one labeled tricky? Because 4th power is a little bit different. It actually has 4 possible answers. But we're going to go ahead and do the first 2 first. The other set of answers has imaginary numbers in it. Oh no! Imaginary answers? We did that like 3 chapters ago. So what does that mean with imaginary? The r can also be plus or minus 3i. We're going to go ahead and do the easy ones first. Let's go ahead and plug in r for 3. So multiply 3 every time. 27 times 3, 81. 81 times 3, 243. 243 times 3 is 729. And just to check your answer, 729 times 3 is 2,187. Let's do it with a negative 3. 27 times negative 3, negative 81. Negative 81 times negative 3, 243. 243 times negative 3, negative 279. And then negative 279 times negative 3 gives us a positive 2,187. All right? But now let's go ahead and look at the imaginary ones. Here's something you have to be reminded of. I squared, when you have I times I, you have I squared. I squared is just negative 1. You have to remember that. All right, let's go ahead and do 3i. Multiply that to 27. You should get 81i. Well, what's 3i times 81i? It turns out that that is 243i squared. But remember, I squared is negative 1, so it's just negative 243. Go ahead and take that 3i and multiply it with this. You should get negative 729i. And then finally, 3i times negative 729i gives you negative 2,187i squared, but then again I squared gives us a positive 1. So that's why the 3i works. All right, and then we also have negative 3i. And let's see how that works. A negative 3i times 27, negative 81i. A negative 3i times a negative 81i squared. A negative with a negative makes it a positive, but then the I and the I makes I squared, which makes it negative again. That's kind of confusing, but that's kind of cool because then you get to use what we knew from a long time ago. And then a negative 3I times negative 243 gives us a positive 729I. And then lastly, just to check, negative 3I times a positive 729I is negative 2,187I squared, but then I squared makes it a positive again. All right, so that one is tricky. Whenever you have r to the fourth power, make sure you remember the imaginary ones as well. All right, quite fun. Go ahead and try the homework.